With respect to these four lines that we've just studied, let's see what happens when we consider certain special kinds of triangles. Let's look at an isosceles triangle, and we've already studied that an isosceles triangle is a triangle where two sides are equal. Suppose AB and AC are equal and the angles opposite to these equal sides are equal. Now, in the isosceles triangle, if I draw the median from vertex A, then this median would actually come down to BC at point D, and when we have drawn the median from this vertex A, which is the common vertex of the two equal sides, this will also be the altitude, this will also be the angle bisector, and because it is the median and the altitude, it will automatically be the perpendicular bisector. Now this in an isosceles triangle is true only for this one vertex A, which is the common vertex of the equal sides. From the other vertices, when we draw the medians and the altitudes, they would be different lines. So suppose I now draw the median from B, then that median would be something like this, and the median from C would be something of this type, and they meet at this common point called as the centroid. Now instead of the median, if from B we draw the altitude, then it would be something of this type, and the third altitude would be something like this. And we would notice that if this is the meeting point of the three altitudes, which is the orthocenter, and if this is the meeting point of the medians, which is the centroid, then these two lie on this same line, and we would find the same with respect to the perpendicular bisectors also, which means if from this point we draw the perpendicular bisectors, and from this point if we draw the perpendicular bisectors, then they would meet at this common point, which happens to be the circumcenter. Essentially what we are trying to say is that in an isosceles triangle, the 4 points that we learned recently, which was the centroid, the orthocenter, the incenter and the circumcenter, they will lie on one straight line, which means that these 4 points will be collinear. This is with respect to the isosceles triangle. Now on the other hand, if we consider an equilateral triangle, and we've already studied that an equilateral triangle is a triangle where all the three sides are equal and all the three angles are equal. Now when we draw the median, it will also be the altitude, it will also be the angle bisector, and it will also be the perpendicular bisector, and that would be true not only for that one median, it would be true for all the medians, all the altitudes, all the perpendicular bisectors and all the angle bisectors, which basically means that this point is not only the centroid, it is also the orthocenter, it is also the incenter, and it is also the circumcenter. So in an isosceles triangle, these 4 points are collinear, whereas in an equilateral triangle, these 4 points coincide. This is true for these special triangles which we have considered, the isosceles and equilateral. We'll now look at a few important theorems with respect to triangles. Let's start with what is called as basic proportionality theorem, or also referred to as BPT. So if we have a triangle ABC, and if we have, suppose, this particular length DE, which is parallel to BC. Now first of all, inside a triangle ABC, if we draw any length which is parallel to the base, we will always get two triangles as similar, which means ADE would always be similar to ABC. Why? Because these would be corresponding angles in parallel lines, and through AA test of similarity, the triangles would be similar. But that is not what we're going to use in BPT. BPT or basic proportionality theorem states that if DE is parallel to BC, then you have AD upon DB is equal to AE upon EC, which is this part upon this part is equal to this part upon this part. Now this is with respect to basic proportionality theorem. But if we want to go beyond and if we want to say that triangle ADE is similar to triangle ABC, triangle ADE is similar to triangle ABC, and if we write the corresponding sides are in the same ratio, then we would get AD upon AB is equal to DE upon BC, which is equal to AE upon EC. So when we look at this triangle ABC, and if we have DE parallel to BC, then BPT would state that AD upon DB is equal to AE upon EC. And then through similar triangles, we can also arrive at these three corresponding sides of triangles being in the same ratio. Let's move on to our second theorem, which is called as midpoint theorem. Now what does midpoint theorem really say? Once again, if we start with a triangle ABC, then midpoint theorem states that the line joining the midpoints of two sides of a triangle is parallel to and half of the third side. What does this mean? If we take the midpoint of AB and the midpoint of AC, and if we join them, let's say this is DE, then line joining the midpoints of two sides, which would be DE, is parallel to the third side and is also half of the third side. So this is midpoint theorem. Similarly, we could have looked at midpoints of AB and BC, which would have been parallel to AC and half of AC. Now in geometry, very often we hear that when there is a theorem, the statement also given to us is converse of the theorem is also true, and hence the converse of midpoint theorem is also true. Now how would we state the converse of the midpoint theorem? Converse says that line drawn from the midpoint of one side, let's say D, parallel to the second side, let's say parallel to BC, bisects the third. So to restate this, line drawn from the midpoint of one side parallel to another bisects the third, which basically means that it passes through the midpoint of AC. So this is how we would state converse of midpoint theorem. Let's look at this diagram. Suppose we label these points now and we know that AB is parallel to EF, which is parallel to CD. Suppose these three lines AB, EF and CD are parallel to each other. And then suppose we say that this length is X, this length is Y and this length is Z. Suppose we say this is A and this is B. So we have these triangles ABC, we have a triangle BDC, we have EF, E is the point of intersection of AC and BD, AB is parallel to EF, which is parallel to CD, and we are now trying to actually arrive at some kind of a relationship between these lengths X, Y and Z. If we know that AB and EF are parallel, then we will know that ABC is similar to EFC. So triangle ABC is similar to triangle EFC, and hence we can very safely say that X upon Y, which is this to this, will be equal to B upon A plus B. We've just written corresponding sides in the same ratio. Similarly, if we say EF is parallel to CD, then we would get BEF, triangle BEF is similar to triangle BDC. And for that, if we write the corresponding sides in proportion, then we would get x upon z is equal to a upon a plus b. Now through these two, if we add them, if we add the left hand sides, we get x upon y plus x upon z. It would be equal to b upon a plus b plus a upon a plus b. If we take the LCM on the right hand side, we would get b plus a upon a plus b, which is the same, and hence the right hand side would become 1. On the left hand side, if I take x common, I would get into brackets 1 upon y plus 1 upon z, and hence the final relationship between x, y and z would be 1 upon x is equal to 1 upon y plus 1 upon z. So whenever you see a diagram of this type where you have three lines parallel to each other, we can safely say that this length x, the reciprocal of that, so 1 upon x is equal to 1 upon y plus 1 upon z. Please note, there is no compulsion for this angle at B and angle at C to be 90 degrees or right angles. As long as these lines are parallel to each other, this property would always be true. Finally, let's look at what is known as angle bisector theorem. Now, angle bisector theorem would be considered in two different parts. One, what is called as interior angle bisector theorem, and the other one, which would be exterior angle bisector theorem. So let's first look at interior angle bisector theorem. If I have a triangle ABC, and if interior angle A is being bisected and the angle bisector meets the opposite side BC at point D, then interior angle bisector theorem states that AB upon AC, which is nothing but the ratio of the two sides of the angle being bisected, would be equal to BD upon DC. Now the way we can very easily remember this, left hand side would be the ratio of the two sides which are being, of the angle which is being bisected. So if angle BAC is being bisected, the two sides are AB and AC, ratio of that would be equal to, from point D, we just continue and we say B up to D. D is the point at which the angle bisector meets the opposite side. Similarly, from point C, we can say C up to D, which is nothing but DC. So this is interior angle bisector theorem. Now in a similar fashion, we can consider exterior angle bisector theorem. And so if we have a triangle PQR now suppose, and if we extend QR, and if this exterior angle PR, let's call this point S, if exterior angle PRS is being bisected, then what we would need to do is extend QP up to a point where it meets the exterior angle bisector. So let's assume this point is T. Let's go through it again. PQR is a triangle. Exterior angle PRS is being bisected. So this angle is being bisected. And this angle bisector meets the other side PQ extended at point T. So once again, if we write the two sides, which now would be RP upon RQ, the two sides of the triangle. So RP upon RQ would be equal to, and similar to the logic used earlier, from P up to the point where the angle bisector meets the third side, and hence up to T, and similarly from Q to that same point where the angle bisector meets the third side, and hence it would become PT upon QT. This is angle bisector theorem, which basically gives the ratio for the two sides of the angle being bisected in interior angle bisector form as well as exterior angle bisector form.